Okay, so welcome back. So let's work a little bit on miscellaneous examples. Example number 21, I didn't really understand the solution. It's a little bit complicated. I couldn't really understand the solution. Example number 22 is basically if A, B, C are in geometric progression. If A, B, C are in geometric progression and A raised to the power 1 by x is equal to B raised to the power 1 by y is equal to C raised to the power 1 by z, prove that x, y, and z are in arithmetic progression. So what this means is that so ABC are in geometric progression, right? Meaning that, for example, B to A is equal to C to B, something like that. And A raised to the power 1 by x is equal to B raised to the power 1 by y, and C raised to the is equal to C raised to the power 1 by z, meaning that the x root of A meaning that the x root of A is equal to the y root of B is equal to the z root of C. Okay? So we want to prove that basically x, y, and z are in arithmetic progression. So what that means is that, so since we have as the solution we have since, or you can say let A raised to the power 1 by x is equal to B raised to the power 1 by y is equal to C raised to the power 1 by z is equal to some k, for example. Then you can say that, then of course here you would have A raised to the power 1 by x is equal to k, which means that basically you have A raised to the power 1 by x is equal to k. That means that basically the x root of A, this implies that the x root of A is equal to k. And so if I raise this to the x power, I get A is equal to k raised to the power x. Right? So we can write this, and also by the same logic, since you have B raised to the power 1 by y is equal to k, that implies that basically the y root of B is equal to k, which means that basically raises to the y power, you get B is equal to k raised to the power y. That is basically another thing. And also we have C raised to the power 1 by z is equal to k, therefore basically the z root of C is equal to k, which means that basically C is equal to k raised to the power z. C is equal to k raised to the power z. And therefore you can say that putting these three together, I can write basically A is equal to k raised to the power x, and B is equal to k raised to the power y, and C is equal to k raised to the power z. That I call number 1. Now since A, B, and C are in geometric progression, since A, B, and C are in are in geometric progression. Therefore, so you can say that b squared is equal to a times c, right? Basically, b squared is equal to a times c. Or you can say that basically b divided by a is equal to c divided by b, which means that if you cross multiply, you'll get b squared is equal to a times c. That you can call number 2, right? And then using 1 and 2, we can basically, we have, using 1 and 2, we have basically, so if b squared is equal to a times c, what that means is that, so b is equal to k raised to the power y. So b is equal to k raised to the power y, and a is equal to k raised to the power x, and c is equal to k raised to the power z. And so b squared is equal to ac implies that basically k raised to the power y whole squared is equal to a times c, which is k raised to the power x times k raised to the power z, and that means that k raised to the power 2y is equal to k raised to the power x plus z, and that basically means that 2y is equal to x plus z. And that basically means that if you have x, y, and z, if you have 2y is equal to x plus c, that implies that x, y, and z are in arithmetic progression, right? Are in arithmetic progression. Now, these kinds of problems, you need to be able to follow, only follow, not find the solution. Sometimes it's not possible. And the first problem, I couldn't even follow this solution. The solution is it's just not possible to understand what they have done. They have not provided the steps, and so sometimes you just can't do it. And so question number 2, example number 23. Example number 23. If A, B, C, and D, and P, if A, B, C, D, and P are different real numbers, such that a squared plus b squared plus c squared times p squared minus 2 times ab plus bc plus cd times p plus b squared plus c squared plus d squared is less than or equal to 0, then show that A, B, C, and D are in geometric progression. A, B, C, and D are in geometric progression. Okay, so we have A, B, C, D, and P are different real numbers, and that is basically some relationship between A, B, C, D, and P. we want to show that A, B, C, and D are in geometric progression. So of course we have basically as the solution we can say that given that A squared plus B squared plus C squared times P squared minus 2 times AB plus AC plus BC plus CD times P, 2 times AB plus BC plus CD times P plus B squared plus C squared plus D squared is less than or equal to 0. Call this number 1. Okay, so from this number 1, the LHS of this gives basically the LHS is equal to basically, if you multiply A squared, so you'll get, multiply all of these in, you'll get A squared P squared plus B squared P squared plus C squared P squared and basically I think we have to multiply all of these in and see what happens really. Negative 2 times, for example, ABP plus BCP plus CDP and then probably, I don't know, plus B squared plus C squared plus D squared. And if I multiply these in, I will get basically A squared P squared plus B squared P squared plus C squared P squared minus 2 times ABP minus 2 times BCP minus 2 times CDP plus B squared plus C squared plus D squared. Then you can basically take, for example, A squared P squared, A squared P squared, this one, and negative 2ABP, negative 2ABP, and B squared together. And if I write that together, I will get basically A squared P squared, negative 2 times ABP, plus B squared. And then you can take together basically B squared P squared and negative 2 BCP and C squared, these two together. And so I can write B squared P squared minus 2 times BCP plus C squared. And then I can take C squared P squared, negative 2 times CDP plus D squared. So I can write basically C squared P squared, negative 2 times CDP plus D squared. And so that should give us basically if I want to write this, I will write this as AP whole squared minus 2 times AP times B plus B squared, right? I can write it this way, and that would be equal to AP minus B whole squared. Of course, as I told you before, these kinds of things, there is no way to know beforehand what you're supposed to do. The only thing that you need to do is just follow the solution. Then there's, I mean, these are, you couldn't even call them tricky things because there is no way to figure them out. But essentially you can follow the solution and learn from some steps, or you can learn things from them. So I can write this as AP minus B whole squared. Then I can write basically BP whole squared minus 2 times BP times C plus C squared, which I can write BP minus C whole squared. BP minus C whole squared. And then over here I can write CP whole squared minus 2 times CP times D plus D squared, which is the same thing as CP minus D whole squared. CP minus D whole squared. And so what that means is that this basically means that the LHS was greater than or equal to 0. That means that AP minus B whole squared plus BP minus C whole squared plus CP minus D whole squared is greater than or equal to 0. You can call this number 2, for example. Now, you can say that since the sum of the squares of real numbers is non-negative, therefore from 1 and 2 we have, so from 1 basically, in 1 we said that this is of course less than or equal to 0. I see, this is less than or equal to 0. This is the LHS. This is less than or equal to 0, and here we have the same thing, greater than or equal to 0. Okay, so this basically means that basically this was the LHS. So here we are saying that the LHS is less than or equal to 0, and here we are saying that the same thing is greater than or equal to 0. Of course, one thing cannot be, for example, simultaneously greater than 0 and less than 0. So the only way that this can be true, which of course is true, both of them are true. The only way that this can be true is to say that basically this expression, or the LHS, is essentially equal to 0, because if I say that one of them is greater than 0, one of them is less than 0, then that would be a contradiction. So that I cannot say. Which means that I can say that basically AP minus B raised to the second power plus BP minus C raised to the second power plus CP minus D raised to the second power is equal to 0. That is equal to 0. Which means that now since this is the sum of all of these equal to 0, that means that all of them have to be simultaneously 0. So if this was something like, for example, AP minus B raised to the second power times, for example, BP minus C raised to the second power times CP minus D raised to the second power is equal to 0, then I would say that AP minus B is raised to the second power is equal to 0, or or basically BP minus C raised to the second power is equal to 0, or CP minus D raised to the second power is equal to 0. Meaning that any of them, if any of them was equal to 0, then the whole thing would be equal to 0. And for the same reason, I would use the connective OR, because then any of them, if any of them were true, the whole thing would be true, right? But since this is addition. In addition, if any of them is not equal to 0, then the whole thing cannot be equal to 0, which means that I should say AP minus B raised to the second power is equal to 0, and BP minus C raised to the second power is equal to 0, and CP minus D raised to the second power is equal to 0. And please note that I have used the connective AND here, because this is addition. And so what that means is that this means that AP minus B is equal to 0. And this means that basically BP minus C is equal to 0. And this means that CP minus D is equal to 0. Which means that all of these are actually equal. Which means that basically you can say that AP minus B is equal to BP minus C, which is equal to CP minus D. And then I can basically take AP then I can take now it seems that somewhere over here we have said that P is equal to something. P are different real numbers. We want to show that A, B, C, D are in geometric progression. And here we have assumed that and here we have somewhere assumed that so then if I say that AP minus B is equal to BP minus C is equal to CP minus D, then what that means is that are different real numbers. Okay, so now we want to show that A, B, C, and D are in geometric progression. Geometric progression means that we want to show that basically A, B, C, and D are in geometric progression, meaning that b to a is equal to c to b, b to a is equal to c to b is equal to d to c is equal to some constant. Call it whatever you want to call it. Call it some k, for example, right? Now, if I assume that I have a, b, and c and d, 4 terms over here, I don't know how they have gotten from here to here, but if I assume that I have a, b, c, and d, so I know that 2 times b, I know that basically, not 2 times b, but essentially b divided by a is equal to, if they are in geometric progression, then b divided by a is equal to c divided by b. Let's call the common ratio as p. Let's call this p, right? So in that case, I could say that then I could write that basically b to a is equal to p, and also c to b is equal to p, which means that basically AP is equal to b, and BP is equal to c, which means that AP minus b is equal to 0, and BP minus c is equal to 0, which is and those are all equal to 0, of course, right? So you can see that I got the exact same thing over here. Of course, I don't really know how they've gotten from here to here. There must be something to do in algebra to get from there to there. But essentially, if you have basically 4 terms or 4 numbers a, b, c, and d, if they are, provided that they are in geometric progression and provided that the common ratio is p, then of course you can say that b divided by a is equal to c divided by b is equal to p, being the common ratio. And then you can write b divided by a is equal to p and c divided by b is equal to p. If you cross multiply, you get AP is equal to b and BP is equal to c. This gives basically AP minus b is equal to 0, BP minus c is equal to 0, which means that these two are now essentially verified, right? And then in the same geometric progression, you can also say that basically, you can also say that c to b you can also say that c to b is equal to d to, for example, or you can just simply say that d to c. You can also say that d to c is equal to p, which means that pc is equal to d, which means that pc minus d is equal to 0. PC minus D is equal to 0, or CP minus D, which means that this is also verified. And therefore, since we have this thing over here, and of course this is a two-way street, meaning that this you can actually think of as an if and only if, right? So this implies that, and that implies that. And therefore, you can basically, from this, you can essentially conclude that basically A, B, and C, you can conclude that A, B to A, you can conclude that, so if you had basically B and A over here, then from this you can conclude that B to A is equal to C to B is equal to D to C is equal to P, and therefore A, B, C, and D are in geometric progression. Of course, I couldn't solve the problem the right way, but that's essentially the essence of this problem. They have done something to get from here to here that I don't know, but essentially we understand what this whole thing means, and that's I think enough. Now these exercises are essentially a little bit tricky. You have to find some way to get around them. Okay, so example number 24. Example number 24, we have if P, Q, and R are in geometric progression. If P, Q, and R are in geometric progression, and the equations px squared plus 2 times qx plus r is equal to 0, and d times x squared plus 2 times ex plus f is equal to 0 have a common root, then show that basically D to P and E to Q and F to R are in arithmetic progression. Okay, so this is not a straightforward question either, but you get to learn a couple of things here, meaning that so P, Q, and R are in geometric progression, right? And these equations have a common root. When you say that two equations have a common root, what that means is that they essentially, the lines, the graphs of the two functions intersect at one point. They intersect at one point. So then you want to show that these three are in arithmetic progression. D to P and E to Q and F to R. So that means that basically essentially you have three numbers P, Q, and R. These are in geometric progression. And using these two numbers, these three numbers, you have created two basically second degree equations. P, Q, and R, and D, E, and F. Right? Now so we already know that the P, Q, and R are in geometric progression, and so we know that basically these two equations have a common root, right? So based on that, we could, if we can of course prove this, we could conclude that basically D by P and E by Q and F by R are in arithmetic progression, which is an interesting situation, really. Okay, so now to show that basically, to show that this is the case, basically what you can do is that this is again not very straightforward, but it's essentially easy to understand the solution. Meaning that you have basically P, Q, and R, which are in geometric progression, and these two equations have a common root, right? And you want to show that basically this is the case, that E by P and E by Q and F by R are in arithmetic progression. So what you can do is that basically you can, of course, so the equation basically we have this equation over here, which is px squared plus 2 times q times x plus r is equal to 0. If you want to find the roots of this equation, you will have basically, you know, that the quadratic equation solution, how you find your x's in there, is that you write, if you have ax squared plus bx plus c is equal to 0, then in that case x is going to be equal to negative b plus or minus the square root of b squared minus 4ac over 2a, right? That is basically how you find the x in such a quadratic equation, which means that your x over here would be equal to basically negative b. So here x would be equal to negative b, which is negative 2 times q, plus or minus square root of b squared, which is 2 times q whole squared, which is 4 times q squared, minus 4 times a, which is in this case p, times c, which is equal to r in this case, right? And you have to divide that by 2a, which is basically 2p. Now, what you can do here is that you can write this as basically negative 2q plus or minus the square root of, and then you can take a 4 out here and write it as q squared minus pr, right? Minus pr, and divide that by 2p, and what that means is that then x is equal to basically negative 2 times q, plus or minus take the 4 out, becomes a 2 square root of q squared minus pr, divide by 2p. And then you can write this as, basically take a 2 out from the numerator. You will get 2 times negative q plus or minus the square root of q squared minus pr, divided by 2p. Now 2 and 2 now you can cancel out, and so your x is equal to, and therefore your x is equal to basically negative q plus or minus square root of q squared minus pr, divided by p. Now since we said that p, q, r are in geometric progression, since basically p, q, r are in geometric progression, we have basically q to p is equal to r to q, which means that basically q squared is equal to pr, which means that basically q squared minus pr is equal to 0. Q squared minus pr is equal to 0, which means that this thing is q squared minus pr is equal to 0, which essentially means that therefore x is equal to basically negative q divided by p, right? Negative q divided by p. Now this is This is the only root of this equation. I mean, the equation has only one root. And we said that over here we said that basically these two equations have a common root. But since this equation, this first equation, has only one root, then we can conclude that the only root that we have gotten is also a root of this equation as well. If this equation had two roots, of course we could not come to that conclusion logically. Now, since here we said that basically these two equations have a common root, and there is no way to know which one. I mean, for example, these two equations are second degree equations, and each of them could have two roots. But since now it is such that basically the first equation has only one root, then that root is going to be common with the second equation, which means that therefore basically x is equal to negative q by p. Negative q by p is also a root of the equation dx squared plus 2ex dx squared plus 2ex dx squared plus 2ex plus f is equal to 0. So we can say that dx is equal to negative q by p is also a root of this equation, which means that this x must satisfy this equation as well, because, well, this is of course a root. So then over here I can write dx squared plus 2 times ex plus f is equal to 0, and therefore set x is equal to negative q by p, which gives me d times negative q by p raised to the second power plus 2 times e times negative q by p plus f is equal to 0. And then we have d times basically q squared by p squared, plus, so you have a negative sign over here, you can take it out, so 2 negative, basically you can write it as 2 times e times q divided by p plus f is equal to 0. And then you can write that as dq squared divided by p squared minus 2 times eq divided by p plus f is equal to 0. And then what you can basically multiply through by p squared to get rid of p squared from these denominators. So you get dq squared minus so times p squared, you would get a p in the denominator, so 2 times eqp plus f times p squared is equal to 0, right? Now here, if I divide by pq squared, we have dq squared by pq squared minus 2 times eqp divided by pq squared plus f times p squared by pq squared is equal to 0. And that means that basically you can simplify these two things, and pq squared and q squared you can cancel, get the q here, p and p you can cancel out, and p you can cancel out with p here, so you'll get p. So what you will get is d by p minus 2 times e 2 times E divided by Q plus F times P divided by Q squared is equal to 0. Now, since Q squared is equal to PR, right? Since Q squared is equal to PR, we have, so you can write D by P minus 2 times E by Q plus FP by basically Q squared is PR. So FP and P can cancel out. You have D by P minus 2 times E by Q plus F by R is equal to 0. And therefore you can take this to the other side of the equation. You can write it as 2E divided by Q is equal to dP plus FR. And that basically means that implies that these are in arithmetic progression: dP, D by P, E by Q, F by R. D by P, E by Q, D by P, E by Q, and F by R are in arithmetic progression, because if they are in arithmetic progression, then of course you know that this times 2 is equal to, meaning that you could write 2 times E divided by Q is equal to basically D by P plus F by R, and that's basically what we have here, and therefore these three are in arithmetic progression, right? And so that's basically this example over here. Okay. Now, so we have basically actually 32 exercises, miscellaneous exercises on this chapter. I think we should do that. It's necessary to do that. We will go through the exercises in the next video. Thank you.